Hello, everyone, and welcome to this CUAHSI Cyberseminar Series, Research and Observatory Catchments, the Legacy and the Future. CUAHSI is very excited to host this series, which was convened by Jamie Shanley, Sebestyen, Julia Jones, and Theresa Blume. My name is Julia Masterman. I'm the Science Education and Outreach Coordinator for CUAHSI. CUAHSI is the consortium of universities for the advancement of hydrologic science, Incorporated, and our mission is to advance water science by strengthening interdisciplinary collaboration, providing critical infrastructure through our data services, and promoting education in the water science at all levels through programs like this Cyberseminar Series. I would encourage you to reach out to me, visit our website, or sign up for our newsletter to learn more about what we do or to get involved. I will add the information for that in the chat in just a moment. This webinar is being recorded and will be posted on the CUAHSI YouTube channel later today. To check out previous week's recordings for this series, visit youtube.com/CUAHSI. If you have any questions throughout this webinar, please put them in the chat. There'll be time for a brief Q&A after each presentation and then a longer discussion at the end. We'll do our best to get to as many questions as possible. Thank you again for joining us this week, and we look forward to hearing your thoughts during the discussion at the end. We've had a lot of great participation in this series so far. We're on week 6. And so thank you for continuing to join us for these Wednesday cyber seminars. This week's topic is forest management and environmental disturbance. And with that, I'll go ahead and hand things off to our convener to introduce the first topic and our speakers. So I believe Julia.
Welcome, everyone. Thanks for joining us. This week's topic is about catchment studies of forest management and environmental disturbance. Many of the oldest paired watershed or watershed studies were established to look at forest management effects, but also many more recently have been established with new objectives. And we are seeing new topics emerging from some of the older studies. And so with that, we'll move to our first speaker. The map shows the catchments that will be discussed today. They're in red dots. So we're mostly in the Western Hemisphere today. Next, please. Our first speaker is Dan Moore, and he'll be talking about forest harvesting and low flows. So Dan, please carry on.
Thank you. So thank you to everybody for organizing this and for all the audience for participating. To start out, I'd just like to note there's been increasing concern about the effects of increasing frequency and intensity of summer drought on low flows and fish habitat. As you can see, this poor rainbow trout got stuck in our weir pond during a severe drought. Next slide, please. Building on this concern, there's a number of studies in the last few years focused on the effects of forest harvesting and post-harvesting forest development on low flows. In particular, there was a very nice synthesis study published by Coble et al. And one of the challenges that they identified in synthesizing the results of past studies is that a range of low flow indices have been used, which makes it difficult to compare across studies. So this study that I've done right now, that I've been working on so far with Kevin Bladen at OSU, really was driven by a simple question: how consistent are the responses amongst low flow indices? Next slide, please. So we drew upon studies from a number of experimental watershed sites in Western North America. I don't have time to go through full acknowledgements, but I'd just like to thank all the people for all their hard work for assembling the data sets and making them available. They're a tremendous resource to the community. And next slide, please. So we assembled the daily stream flow data from all those studies, and we computed for each site a number of low flow indices: the 1-day low flow, 7, 30, and 60-day low flows for the July to September period, the total yield for July to September each year, and the number of low flow days. And this is computed for the period May to October, and we used as a threshold any flow less than 10% of the long-term mean annual discharge to have a consistent threshold across studies. I'm going to present results that I've cherry-picked from 4 studies, given the time constraint. This first example is from Watershed 6 in the H.J. Andrews watershed. The watershed was 100% clear cut. And what the graphs show is the red line is the difference between observed and predicted from the pre-harvest regression. The gray ribbon are 90% prediction limits for new observations computed from the fitted pre-harvest regression. The vertical gray lines mark the beginning and end of harvest, and we've standardized them also the time series. Year 0 is the end of harvest. Now, in this example, you can see that there's a fairly consistent response amongst the low flow indices, and there's a good consensus that there's a flow surplus about the first 20 years or so, shifting to flow deficit by about year 22. Next slide, please. This next example is Casper Creek, South Fork, and you can see that flow surpluses developed during the harvesting period, but then shifted quite definitively to flow deficits about 5 years or so following the completion of harvest. And again, this response is consistent amongst low flow indices. Next slide, please. So this shows watershed 1 in the H.G. Andrews, and again, is 100% clear cut. This response is a bit more interesting. You can see that, like Casper Creek, flow surpluses developed during the period of harvesting. And like Casper Creek, they only persisted for about 5 years following harvesting. But there's an interesting difference between the short-term indices like the 1-day and 7-day low flows and the longer-term indices like the yield and the number of low flow days over the warm season. In particular, for the shorter-term indices, they definitively go into flow deficits between about 5 and 10 years following harvest, whereas they don't definitively go into deficits until about 32 years for the longer-term deficits. So it suggests there may be some very interesting processes to follow up on. Next slide, please.
You've got 220, Dan.
Okay. Next slide, please. Okay, so this is watershed 3 in the H.G. Andrews, and it was 30% patch cut. Like some of the others, you can see that the responses are qualitatively similar amongst the indices, so there's a good consensus. But an interesting feature at this site is that about 15 years to about 24 years following harvest, it goes from a flow deficit to neutral situation, then back to surplus, and then finally going back to deficit. Now, interestingly, the onset of this period of neutral flow effect it coincides roughly with the onset of the late 1970s shift in Pacific decadal oscillation, which suggests there may be some interesting interactions between climate variability and the stand evolution following harvest. Again, this is another question that might be worth following up on. Next slide, please. So in summary, this research just started with a very simple question, and it really follows on what Tim Burt said in the first of these series. That is, it's worthwhile going back to these existing studies with new questions and to come up, perhaps generate new hypotheses, questions to follow up on. And in this particular case, I think that what we've identified is there's some interesting idiosyncrasies of the responses to low flows to harvest, and that it's worth following up, and we may actually learn a lot more from this. So thank you very much for your attention.
Great. Dan, we have about a minute for questions. Are there any in the chat?
We don't have any questions yet. If anybody would like to quickly type one in, we might be able to address it. Otherwise, we might want to move ahead.
I'll just comment while we're waiting that this is a beautiful example of some of the kinds of synthesis that we hope that this catchment series will stimulate, and that we hope to talk about more in week 8.
Mm-hmm.
And again, I encourage everyone to pay attention to the chat and enter your questions early, so we have a time to address them if there is time left. Kevin Bishop just wrote, does this mean that harvest gives both floods and droughts? Just a matter of when you look?
Do you want me to respond?
Yeah, please.
Okay.
Yeah, well, I think that, of course, it's been very contentious about the effects of forest and floods, and I don't even want to touch that discussion right now. But I think that as Kovalov synthesized, there's this emerging consensus that at least at some stages during post-harvest stand development, there are periods of flow deficits that develop. And I know that the managers in British Columbia are starting to get very interested in this.
Thank you, Dan.
Okay, we should move on.
Yeah.
Our next speaker is Paul Richardson, who will be talking about experiments from Casper Creek in Northern California. Paul, take it away.
Hi, everyone. I'm Paul Richardson. I'm a postdoc with the Forest Service in Northern California. Thank you for attending today. I'm going to be talking about Casper Creek and 3 harvests and 3 lessons that we've learned. Next slide, please. The Casper Creek Experimental Watersheds is located in Northern California. It receives just shy of 1,200 millimeters of rain annually. Snow is rare. The climate is mild. Next slide, please. Monitoring began in 1962. The experimental watersheds includes two, the North Fork and the South Fork. They're both heavily instrumented and include weirs at their outlets. Next slide, please. The Casper Creek watershed is primarily a second and third growth coast redwood forest. This is what you'd see if you went out hiking through the South Fork. You can also see a coast redwood stump in the foreground. That stump would have been from a tree that was cut over 100 years ago. Next slide, please. Casper Creek was logged of old growth trees from 1860 to 1904. This is a photo that was taken circa 1870. You can see an oxen team that's pulling logs out of a catchment. Next slide, please. There have been 3 experimental timber harvests at Casper Creek. The first harvest was in the South Fork from 1971 to 1973. It was a selective harvest and it was primarily completed through tractor yarding. The second experimental harvest was in the North Fork from 1989 to 1992. There was some harvesting that happened too in the North Fork in 1985, 1986, but it was not part of the experiment. In that second timber harvest experiment, they focused on clear cutting subcatchments. Most of that was completed through cable yarding. You can see a cable yarder in that middle photo. There'd be a cable that would run down to the bottom of the hillside. Cut logs would be connected to it. They'd be pulled up to this platform. You can see logs that are stacked on it and then hauled out. We just completed a third harvest in the South Fork from 2017 to 2019. It was a selective harvest. It's mostly completed through cable yarding too. However, in this photo, you see a feller buncher up on a hillside that's cutting trees and stacking them. Next slide, please. So today I want to focus on 3 lessons. And I think that many folks will find that these lessons are not unique to Casper Creek and ring true for many other sites. So the first lesson is the most interesting results are often unexpected. In a recent paper we published in WRR, we report on findings that bedload transport decreased following the North Fork timber harvest. In this plot, you can see gravel departures versus year, where the gravel departure is the predicted yield minus the measured yield. The predicted yield is predicted with a Wilcox 2-fraction bedload transport model focusing on the gravel fraction. The measured yield is reconstructed gravel yields from annual weir pond data. And I want you to focus on this period. So in this this plot, you can see a cumulative gravel departure in this black line. And you can see this major departure that happens after harvesting happened in the mid 80s and early 90s. And that departure is showing that the model over-predicted yields. And we think what happened was that there was an increase in gravel storage and less efficient gravel transport that happened during this period. This was due to a series of blowdowns that happened following the timber harvest along buffer strips. These trees were recently exposed. Large storms came through, blew the trees down, substantially increased the wood yields in the streams. In this photo, you can see a log jam downstream with substantial gravel storage upstream of it. Next slide.
2 minutes
please.
15, Paul. 2:15 to go.
Thank you. Next slide. Lesson 2, post-harvest recovery can take not only years, but decades. So here's some more Casper Creek low flow results. On the y-axis, we're looking at observed summer low flows versus low flows that were predicted with an antecedent precipitation index and compared to year. And when the value is above 1, it shows that low flows have increased. When it's below 1, it shows that low flows have decreased. I've marked the years when harvesting occurred and also thinning. But for the South Fork, you can see that there was a response that took on order of a decade. First, low flows increased in the summer, then they decreased. The North Fork, the response took multiple decades. There was also some thinning in there that likely extended it. Next slide, please. Next slide, please.
You're not seeing it advance?
I'm not seeing an advance.
Shoot, it's advancing on my. Okay, sorry about that.
It's all right.
How about now? Am I in the right
now we've
spot?
got to the end.
Back up,
Yeah, if you can back up maybe
Oh.
2 slides.
backed up. I'm looking at lesson 2 now. Not seeing
Okay, I
it.
see lesson 3. Okay, one more slide, please. All right, perfect. Oops.
Yeah, it's slow reaction. I must have a bad connection. What do you
Well,
see now?
the best you can, you might just want to try to address your points or you're going to be out of
Okay.
time.
So lesson 2, the expanded lesson from 2 is that post-harvest recovery can take not only years and decades, but also potentially centuries at Casper Creek. We have trees that live to be thousands of years old. They are the tallest trees in the world, coast redwood. They are over 100 meters tall. So wood recovery to the streams could take a substantial amount of time. And lesson 3 is that public interest remains very high in timber harvest studies. And we might make it, here we go. These are just some recent headlines that talk about, comment on plans for future timber harvest in the Jackson Demonstration State Forest, and also comment on our last experimental harvest at Casper Creek. And if you're interested in Casper Creek data, we've made much of it available online. Please check it out. And I just want to thank CAL FIRE for their continued support in maintaining Casper Creek. They've been involved since the beginning in 1962, and they continue to be devoted to the experiments out there. Thank you.
Okay, are you seeing, thank you. Are you seeing talk 3 now?
Yes.
No? Yes? Okay, if this keeps messing up, I'm gonna have to, someone else might have to take control.
We're seeing a list of talks, and the
Yep.
next speaker is John Whiting, who will be talking about the Kings River watersheds in the Sierra Nevada. John, please go ahead.
Thank you, Julia. All right, my name is John Whiting. I am a geologist with the USDA Forest Service Pacific Southwest Research Station at the Kings River Experimental Watersheds, or CREW. I am excited to tell you a bit about our watersheds here in the Southern Sierra Nevada mountains of California. Next, please. I'd like to acknowledge the researchers who started our project in 2000, Carolyn Hunsaker, Dale Johnson, Dave Herbst. Currently, our team consists of Joe Wagenbrenner, David Drawley, Kevin Mazzocco, Megan Arnold, and myself. We also depend on our many collaborators, especially Safiq Khan and the UC Merced Sierra Nevada Research Institute. Next, please. Our funding and network of collaborators come from national, state, and local levels. Our catchments are managed primarily by the Sierra National Forest, with remaining land owned by Southern California Edison. Next, please. The primary goals of CREW are to, 1, quantify the variability in physical, chemical, and biological processes of Sierra Nevada forest headwater ecosystems, and 2, to evaluate the impacts of prescribed burning and forest thinning on these processes. Next. CREW consists of 2 sets of 4 primary study watersheds and an integrated watershed. The bull watersheds are higher elevation and snow dominated, with approximately 560 millimeters of discharge. The Providence watersheds are lower at the rain snow transition, with approximately 367 millimeters of discharge. Each of the watersheds in each set has either been treated with prescribed burning, mechanical thinning, both burning and thinning, or is a control. The watersheds range from 49 to 228 hectares. They are underlain by granodiorite and quartzite and receive a mean annual precipitation of 1,330 millimeters. Next. We continuously monitor discharge and sediment flux at the outlet of each watershed. At the top and bottom of each set of watersheds, we have MET stations with snow pillows at each of the upper MET stations. Next. And next. Besides hydro and meteorologic data sets, we also conduct repeat watershed scale surveys of vegetation and soils. Next.
You have about 3 minutes and 20 seconds.
Great, thank you. And next. And 19 years work at CREW has contributed to approximately 50 publications. Some highlights are stream flow is dominated by subsurface flow following rapid infiltration of rain and snowmelt through preferential pathways. Also, runoff ratios are higher at high elevation catchments due primarily to decreased evapotranspiration. Benthic invertebrates respond most to decreases in flow. During drought, the population increased, but diversity decreased. And finally, regolith thickness is greater at the lower elevation catchments than the higher elevation catchments. And this greater thickness generally results in more groundwater storage, which is expressed by more chemodynamic streams. Next. All right. Immediately following thinning treatments and between burning treatments, California was hit with a major drought. This provided the opportunity to see how the treatments influenced tree mortality. The treatments were generally light, and determining impacts on the ground were difficult, but using streamflow data and satellite imagery of vegetation greenness, Bart et al. Were able to detect treatment effects on streamflow and tree mortality. By mass balance and ignoring soil surface evaporation, water that might have been used by vegetation removed during treatments may A, contribute to increases in streamflow, as well as contribute to increases in transpiration in remaining trees, thus protecting those trees from drought stress. Or excess water in the system may only contribute to B, increases in streamflow, or C, increases in transpiration in those remaining trees. Next. And next. Bart's findings indicate at the lower watersheds, streamflow increased in response to treatment with no discernible impact on tree mortality. At the higher elevation watersheds, however, tree mortality decreased in response to treatment with no discernible effects on streamflow. Bart et al. Hypothesized these contrasting responses may result from observed differences in regolith thickness between the sites, generally larger at the lower elevation catchments. This might impact root structure and flow paths, and thus the partitioning of excess water in the system. Next. Much of CUAHSI data is available online. Some real-time meteorology data is available on California's Data Exchange Center. Next. And next. Our post-treatment data collection is ongoing at CREW, and we are excited to begin developing our next set of experiments soon. As always, we welcome collaborators. Next. And thank you. And thanks, Jamie, for helping me out.
I'm glad it worked. Okay, we have about 20 seconds for questions.
We don't have any questions that have been posed to John yet. So perhaps we should just move ahead and keep on schedule.
Okay.
Our next speaker is from the middle part of the United States. Kenton Sena will be talking about coal mining disturbance in watersheds in Kentucky. Kenton, please carry on.
Hi, everyone. Thank you so much for putting this together. I'm really excited to be able to participate and share a little bit about our work at Robinson Forest. So Robinson Forest is our research forest in Eastern Kentucky. It's managed by the University of Kentucky, and I'm sharing today some of the work that, that we've been doing recently to collate, compile, release, and analyze some of our historical data. And I'd like to especially acknowledge my co-authors, Chris Barton and Tanya Williamson. Next, please. So a little quick history about the forest. Robinson Forest was acquired by the University of Kentucky in 1923. Prior to that, it was just about completely clear-cut logged. So it was logged in the early 1900s prior to being acquired by UK. Some of the first stream instrumentation that went in were weirs on a couple of the watersheds, Falling Rock and Little Millseat. I'll talk a little bit more about these in just a little bit. There were also a series of precipitation gauges that were set up in the early 1970s, and bulk deposition started to be collected for chemical analyses in the early 1980s. A number of studies have taken place at Robinson Forest over the years, including some important streamside management zone best management practice studies, and ongoing work investigating stream permanence and effects of surface mining and surface mine reclamation. We also have some streams that are designated reference in this region, and so they're used for a variety of water quality and macroinvertebrate community analyses and other sorts of analyses as reference streams. I did want to highlight that we recently compiled data from 4 streams, Coles Fork, Clemens Fork, Little Mill Seat, and Falling Rock. We also collated and compiled and released data from 6 precipitation stations on the forest. Those data have been released via USGS Science Base, and we have a data note in the special issue that highlights that release. Next, please.
You got 320 left.
Thank you so much. So this is the forest today. So in addition to those basins that I mentioned, at this point, we now have 16 streams that are instrumented with weirs and or flumes, as well as some additional sub-watersheds that were instrumented with temporary flumes at different points of time. We have a total of 15 precipitation stations that are set up. Some of these are both precipitation depth and chemistry, and some of them are just bulk depth collectors. Of the sub-watersheds at Robinson Forest, we have a variety of different kinds of influences, including some that have been affected by surface mining. And that's what I want to talk about a little bit more today. And I wanted to also especially highlight that we do have a bunch of historical data that we've not yet compiled and released. And that's a next step for us, is to get those data pulled together and released for to be available for analysis. Next, please. Recently, we were able to upgrade some of the facilities at Robinson Forest thanks to some funding from the NSF. And I just wanted to highlight, we've got these new gauges at some of the weirs that are able to transmit stage height data real time. And we're still working on the process or pipeline for making those data formally available. And then we also were able to establish mesonet weather stations at 2 sites in our system, and these data are publicly available via Kentucky Mesonet's portal. Next, please. So what I wanted to talk a little bit more about is the effects of surface mining and some of the challenges related to that. So Robinson Forest is uniquely situated geographically to help us explore potential effects of surface mining on streams, especially. This figure on the left shows the outline of Robinson Forest. In this figure, the purple reflects surface mining activity and the green is forest. And I wanted to especially draw your attention to the purple area at the northernmost part of the forest. You can see how some of that purple extends into the forest. These are some of the sub-watersheds at the headwaters of Clemens Fork. And on the right, you can see a figure that shows sulfate, mean annual flow-weighted sulfate concentrations in streams between Clemens Fork and Coles Fork. Coles Fork is our control watershed that has had no timber harvest or surface mining influence since it's been owned by the university. And you can see in the mid-1900s, there's a strong departure where Clemens Fork, sulfate concentrations in Clemens Fork start to rise. And I just wanted to highlight that as coinciding with the timing of the surface mining activity in the headwaters of Clemens Fork. So
15 seconds.
So sorry, this is something we're continuing to explore. Next, please. I will skip over this slide for the sake of brevity. And then I wanted to also highlight that there's been a tremendous amount of reforestation work that has been done on Robinson Forest and the surrounding area to explore techniques for establishing forests on surface mined land. So thank you so much for your time.
Thank you, Kenton. I think we need to move on to the next speaker, Julia.
The next speaker is Catalina Segura, and she will be talking about long-term watershed experiments in the Pacific Northwest of the US and Oregon. Carry it away, Catalina, please.
Thank you very much for this opportunity to the organizers for this very stimulating series of talks and for the chance to talk to you today. I will be discussing some of the analysis we've done of runoff response to harvesting of old growth forest based on long-term hydrometric records in the Andrews Forest in Western Oregon. I'd like to acknowledge my co-authors, Emily and Julia, and I'm only going to present some of our results most of them are going to be included in the special issue that hopefully is about to come out. So next, please. The Andrews Forest includes 8 experimental watersheds, and some of them are located at low elevation, some of them located at high elevation, as you can see in the map in the right. The records in the Andrews started in the 1950s for watersheds 1, 2, and 3 in the lower south end of the watershed. In 1963 for watersheds 8, 7, 6, and 8 in the north in the high elevation watersheds. And in 1968 for watersheds 9 and 10, also located in the south of the watershed. The vegetation in the Andrews in the 50s was mature and old-growth conifer forest, and with ages varying between 125 and 500 years old trees. The watersheds were treated in the 60s for watersheds 1 and 3, and the 70s for watersheds 6, 7, and 10. And so now we have planted Douglas fir forest in these treated catchments that are around 50 years old. Some of the watersheds were also subject to road construction, and some were affected by debris flows triggered by our flood record in 1996. Next, please. Some of the prior work indicates that there's an initial increase in peak flows post-harvest, as some of the previous speakers have mentioned. And later on, based on a longer time record, we have found that there's a decline in summer flows 25 years after the harvest. In addition, climate change has resulted in declining snowpacks in the region. And so we revisited some of the long-term records again, and with some hypotheses in mind. So we thought that we were expecting to see changes in transpiration and interception as the planted forest grew. We were also expecting to see changes in snowmelt amount and timing driven by changes in vegetation canopy and structure. And we also expected to see the effects of roads and debris flows triggered by, again, that flood record. So our approach included analyzing over 1,200 storm events between 1958 and 2017. We separated quick flow and delay flow and examine changes over time of runoff ratios. So we looked both at runoff ratios of quick flow and runoff ratios of delay flow. Next, please.
You have 2 minutes and 45 seconds.
Thank you. The question that is behind all of these is, what is the value of having these long-term records in these per watershed experiments? And I'm going to give you 2 quick results. Next, please. So if we think about the 50-year response to fall storm events after clear cutting of these old growth forests and replanting with Douglas fir, the first thing that I want to clarify is that all these fall events occur when the watersheds are just wetting up after a long dry summer. We found that the response was similar across all watershed pairs, despite differences in snowpack, roads, and debris flows, and that can be seen here in this graph in the right. We found that 40 to 50 years after the harvest, delay flow was 50% lower in the plantation than in the reference old growth, and that can be seen here with the green line. So the green line is the delay flow, and the brown line is the quick flow. And the interpretation for this is that high transpiration from planted forest during the summer depleted soil moisture, and then that also results in reduced base flow also in the fall. And so what is interesting about this work that we're doing is that we're moving on from only thinking about the low flows in the summer, trying to see what happens in other seasons. And so in the next slide, please, we can look at the response of in the events in the winter and the spring. And we found that in the winter and spring, the storms now, they occur when the watersheds are wetting up. And we found that the response differs among watersheds. And I'm going to highlight some of the differences we found. So watershed 3, which was subject to roads constructed in 1959, had associated road debris flows in 1996, we see that quick flow was 20% higher in the 4th and 5th decade compared to watershed 1, which was not roaded. And so this is a clear effect of the roads themselves. And this likely results because the changes in routing as the debris flows scour the channels and result in increased network connectivity. And studies have actually documented this interaction between the flood and the roads. Something else to highlight is in Watershed 7, which is located at high elevation, we see that the lay flow was lower than in the reference mature forest. And we believe that this is a result of having greater initial snowpack accumulation and more rapid melt in the canopy gaps during the winter, but then this effect got diminished as the increase in dense canopies of 30 to 50-year-old forests intercept more snow than the mature old growth. In addition, it's also likely that some of these trees are opportunistically evapotranspiring in winter and spring, accessing water that is stored in the soil. There's a lot more things that we can discuss from this graph, so we don't have time. I just encourage you all to follow up with our paper that hopefully is going to come out soon. Next, please.
We are out of time.
Okay, so
Yeah.
I'm going to leave you with this slide right here. And can you just hit next, please? I just want to say that all of this is not possible without the robust framework of data collection and management in the Andrews Forest. And I just wanted to highlight some of these very important people who collect and manage our data.
Great.
Am I out of town? Okay, sorry.
Yes. It's good, thanks. Okay.
Thank you, Catalina. Our next speaker is Johnny Boggs, and he'll be talking about species conversion in North Carolina. Go ahead, Johnny.
Hello, everyone. It's good to be here. My name is Johnny Boggs, and I'm a biological scientist with the Forest Service Southern Research Station in Durham, North Carolina. I'm going to present results from our watershed studies in the Piedmont of North Carolina. The studies will look at tree transpiration, stream flow in connection with forest management practices in the region. Next. This figure is from the Southern Forest Futures Project that was published in 2013. The southeastern US is really kind of the wood basket of the world with millions of acres of natural pine, oak pine, and upland and lowland hardwood forest. In the 1950s, there were almost no pine plantations in the southern US. Now there are over 40 million acres of planted pine, with almost all of that expansion occurring probably over the last 25 years or so. So as you know, land management practices that include converting land from hardwoods to pines to meet the rising demand for wood can have consequences for surface water availability. And so in some of our work, we want to quantify that change in surface water availability. Next. So the red square on the map in the bottom left shows the location of the study sites. They're in the Piedmont region of North Carolina at an elevation of about 150 meters. The paired watersheds range from about 12 to 40 hectares. There are two watersheds at Olmsted Research Farm, which is owned and managed by North Carolina Department of Ag and Consumer Services. And then we also have a site at Hill Forest, which is owned and managed by NC State. Next. So the activities that occurred in the watershed are shown in the tables. After the clear cut, the treatment watersheds were site prep for planting pine, which included also a herbicide spray and then a control burn. The pines were planted in 2012. And then the most recent activity occurred in December of 2019, and that was a thinning. Next. So we actually started collecting data in 2007 as part of a larger BMP project with North Carolina Forest Service. And like a lot of research projects, once you address one question, other questions will come up and they require data. So here's a list of some of the data that we've collected since 2007. Next.
You're just a little over 3 minutes left, Johnny.
Great, thanks. So this figure here shows basal area for the control and treatment watersheds from 2015 to 2020 at Hill Forest. As you can see, there's little change in the basal area on the control watershed. And then you contrast that with the treatment, you see this rapid increase in basal area for the young pines over time. And after that December 2019 thinning, you can see basal area decreased from about 25 square meters per hectare down to about 10. And so we thinned that site from about 80 trees per hectare to about 150 trees per hectare. Next. So this figure here is some of our transpiration data. It compares sap flux density from a 7-year-old pine stands, and these are loblolly pines at Hill Forest, and we planted shortleaf pine at Olmsted. So here's 7-year-old pine stand compared to 45-year-old trees in the controlled watersheds, and this was at Hill Forest. So sap flux density in the 7-year-old pine stand was 2 times higher than the 45-year-old pine stand. And so, of course, as trees get older, they cannot transport water as efficiently as they used to. Next. So this graph here shows the differences in sap flux density between loblolly pine, which is Pinus tita, and then shortleaf pine, which is Pinus echinata, and this is at Olmsted. So you can see sap flux density in the loblolly pine trees was about 20% higher than the shortleaf in 2018. And in North Carolina, 2018 was a really wet year. We got about 1,800 millimeters of precip. In a normal year, we get about 1,100 millimeters. And then in 2019, sap flux density was about 50% higher for the lob trees compared to the shortleaf. Next. And then this figure here, which is my last figure, it shows the annual % change in stream flow after the harvest in the treatment watersheds. So a few takeaways from this. In year 1, we observed a pretty dramatic increase, about a 200% increase in stream flow at both Hill Forest, which is the blue bars, and then Olmsted, which is the green bars. Of course, this means that flow was about 2.5 times what it would have been if we had not cut the trees. And then by year 8, the dramatic increase had diminished. And then by December of 2019, annual water yield was 6% less than pre-harvest levels at Hill Forest. A species conversion study by Wayne Swank and others in the mountains had different results. And so in conclusion, again, we saw a 200% increase and differences in water use across species. And I'll stop there. Thanks.
Great. Thank you, Johnny. I just want to remind everyone that we have a pretty lively discussion going on in the chat, so please do check in there. Previous speakers have been able to respond to questions asked. If we have, oh, looks like we're going to move on to the next speaker. Johnny, there are a couple questions in there for you to address if you want to.
Great.
Great, thanks, Johnny. Our last 3 talks are all from Chile. The first talk is by Francisco Balocchi about watersheds managed by the Arauco company. Carry it away, Francisco.
Hey, thanks, Julia. So thanks to everyone for attending. So I am talking about this, our research catchment network inside the Arauco company. I completely forgot to put my email in the entire presentation, so sorry about that. In any case, my email is francisco.balocchi@arauco.com. I will post that probably in the chat, but just in case. Next, please. Just a very quick note. I work in Bioforest. Bioforest is the R&D institution of Forestar Arauco, which maybe you know, is one of the largest forest company worldwide. And since 2008, the forest hydrology program arise inside the company, and we start to establish a network of catchments. I will show you that later, and in different forest types, and also just be within the coastal range. I will show you that in the next slides, and also because we are too big, of course, we are affecting a lot of things inside the ecosystem. We have this water strategy, and we have 4 mainstays. And one of them is the to know mainstay, and that means basically what we do inside bioforest, which is the research behind some of the decisions of the company. Next. So our objective, it was to improve our understanding of what is the role of the plantation, of course, on the water balance, what is the effect of planting to the nearby communities. So as you can see, specifically, we have a set of plots I'm showing later also that are quantifying the component of the water balance. So we have LoRac data. We try to capture the main sources of variation. We have different forest types, different ages, and through different locations in this huge region, of course, calibrate models, and mainly, and we're the last part of a huge project inside, local demonstration for communication. Next, please. So this is our data node. We present, because we have ordered this data, putting together 10 catchments that are around 20 to 110 hectares that cover from the 35 to 39 south degrees. So if you're not familiarized with Chile, you are not. We're talking about from the semi-arid coastal zone, which are around 800 millimeters of rainfall, through the center, which is the humid zone with around 1200. Then a zone in the south with around 200, with the zone near Valdivia. All the catchments are rain-fed, but we have 16 catchments. So we are compiling more data to share, but this first data node in the company is just for 10 catchment. And also we have more data. I will show you later also what data we have. Next.
You have 2:15 left.
Okay, great. Almost done. Almost done. Okay, this is next, please. So this is a quick example that we have. This is just some hydrograph. I plot here the runoff coefficients, so streamfall over precipitation. As you can see, obviously in the semi-arid region, very low runoff coefficients. You have a lot of runoff coefficients in the center, just because Untitled is a very thin soils, and more or less similar in the south. Next one. Using this data set, and the reason that we are showing just until 2016 is because we have a very huge mega fire in January of 2017. So this is a paper that we published in Forest College and Management. And as you can see, it's pretty unusual. So we don't know, basically, we think that we expected an increase in stream flow, like many studies around the world, but it doesn't in the catchment. So even though there are few cases around the world, it's still unusual, and we want to put up more explanation. As you can see, more than the 50% of rainfall is not accounted by the evapotranspiration or by the streamfall. So it's a very interesting thing. Next one, please. The extra data that we have, that we are hopefully posting someday in the web, we have our soil mapping. We have texture, organic matter, carbon and nitrogen content in 19 by 19. We have the DEM 5 by 5, 1 by 1. We have a lot of subflow data from native forests, pine plantation, and eucalypts in all these things. We have some groundwater levels in these catchments, soil moisture sensors and some plots. And also we have some treatment data. All this data is around 54 plots and range between these locations. And thanks.
Thank you, Francisco. We have to move on.
Great. Let's go on to the next slide. You'll notice that the first few, many of the first few talks in this series are about forests planted in predominantly public lands, but the last half of the talks, including the ones from Chile, are about forest plantations on private land. And this next talk by Antonio Lara is about a restoration experiment.
Thank you very much. I'm really glad to be in this seminar, and I acknowledge my co-authors, Julia Jones, Christian Little, and Nicolas Vergara. Next, please. So forest plantations have expanded a lot in Chile and in many other countries of South America and other regions. And the research questions that we posed were, how does streamflow respond to early stages of restoration of native forests in former eucalyptus plantations, and how these restored watersheds compare to another watershed that remained as eucalypt plantations? Next, please. So this is our study site in South Central Chile, and it receives 2,500 millimeters of precipitation a year. And in the red arrows, you can see the 3 restored watersheds that we considered, and with the blue arrow is the one that remained with eucalypt plantations. Now on the right, a series of panels, you see how this evolves through time. So we have the pre-treatment period 2006 through 2010, the clear cut of eucalypt plantations and native trees planted north of Augustin Bay in 2011. And then we have how the restoration progressed since 2011. Next, please. So the instrumentation, where we have several precipitation records, and also we have automated continuous observations since 2009 on. Next, please. Here you see the progression of the restored watersheds. And as you can see, the restoration was quite successful. I don't have time to present the results here, but it was a complete cover of natural species, not only the planted one, but 15 species, other tree species. And we see this as forest restoration to happen in a long term, I mean, over 200 years. Please, the next one. So some of the key results is, and I will refer to annual streamflow response to clear cut and planting of native forest species. And as you can see in chart B on the lower chart, a blue line is precipitation, and then the bar are the watersheds, the catchments. And you can see that in the this was done with the before-after control impact analysis using the relationship between precipitation and streamflow in the pre-treatment period, i.e. 2009 and 2010. And then you see a big increase in the treated watersheds, and also in the later period. Next, please. There is an important difference among seasons, and the main increases happened in fall and summer. And in summer, in panel D, as you can see that these increases can be in some watersheds up to 150%. But also, very interestingly, there has been very dry summers in Chile in 2014 and 15 in this part of the country, and that meant very important decreases in streamflow in years in those years during summer. Next one, please.
2 minutes to go.
Yeah. So this chart shows what happened with base flows. So in years 2017, 2019, as you can, the last 3 years, that's you can see that how annual base as a percentage of total flow was consistently higher than the long-term mean catchments, but not in the in the catchment that remained as eucalypts. That's the one, the orange part. And we explain this as that plantations may have depleted deep soil moisture reservoirs, and the removal of eucalypts may have permitted recharge of deep soil storage moisture and gradual recovery of base flow. Next, please. So I will skip this one and leave you these key findings and outcomes for the ones who see the presentation later. And the next one, please, the last one. So our conclusions are that this is the first study to test streamflow response to native forest restoration in former eucalypt plantations, and that native forests and the restoration will continue to change and affect the stream flow in the future. We're only seeing the initial period, that maintaining long-term catchment studies is a major challenge in Chile and in many countries of the global south. And finally, that there is a need to continue and expand the long-term catchment forest studies in Chile and elsewhere in the global south. And my last message, that needs data sharing and training and scientific collaboration. So thank you very much.
Perfect timing.
Yeah, I think we should probably just move on. We're honing in on the last talk, and we're going to cut into our discussion time if we don't move ahead. And just a reminder, we are going to have a 15-minute discussion at the end, so please do keep your discussion topics coming in through the chat, and we'll address as many as we can.
Thanks to the speakers. Our last speaker is Andres Irome, who will talk about catchment research on private forest lands in Chile. Go ahead, Andres, please.
Thank you. Good afternoon to everyone. Thank you very much for the possibility of introducing our research. More details of this research are in an article co-authored with Julia Jones and James Bathurst, submitted to the special issue. But in this presentation, I also include the names of Álvaro Zapata and Rebecca Sangüesa, professionals from Forestal Mininco. Next, please. Forestal Mininco is one of the most important forest companies in Chile, and the company has just celebrated the 101 anniversary. Forestal Mininco supports the research and manage the instrumentation. They use the data to assess compliances with forest certification processes, prevent and mitigate undesired downstream effects, ensure sustainable forest and ecosystem management, promote collaborative research, and provide outreach. Below, some photos with discharge gauging station, V-notch weirs in catchment up to 300 hectares, rectangular section in catchment over 400 and up to 800 hectares, and natural sections in catchment with more than 2,000 hectares. Next, please. The experimental catchments are in 3 different sites, all between 37 and 38 degrees latitude south. Escuadrón is near the Pacific coast, Nacimiento in the eastern aspect slopes of the coastal mountain range, and Rucamanqui in the foothills of the Andes Mountains. At the Nacimiento sites, 11 catchments between 7.7 and 414 hectares, instrumented in 2008, discharge and precipitation, rainfall partition and plots, soil moisture, suspended sediment, isotopes in a research with Catalina Segura, and 2 additional catchments in 20 and 20 with more than 2,000 hectares each. At the Rucamanqui site, 2 catchments between 200 and near 300 hectares instrumented in 20 and 20, and at the Escuadrón site, 3 additional catchments between 77 and a little more than 700 hectares instrumented in 20 and 20. Next, please. The 3 sites are in an area with very high concentration of forest plantations. The figure on the left shows in red where these plantations are located. Plantations are mainly with radiata pine, the Monterrey pine, and eucalyptus species, mainly globulus, nitens, and hybrids in the last years. Rotations are in the order of 22 to 24 years for pine and 10 to 12 years for eucalyptus. The figure on the right shows a detail of the 11 Nacimiento catchments instrumented in 2008. They are covered with eucalyptus and pine plantation established in 2000 or later. This area has been in active forestry since the 1960s, where the first pine plantations were established on very eroded and degraded soil. Next, please.
You have just 3 minutes, Andres.
Okay, thank you. I have time. Forest treatments include clear cutting and replanting with eucalyptus or pine, thinning of pine, various riparian buffer width, even age, and mosaics plantation management approaches. The photo below right shows a couple of nested catchments with 42% of the area covered with native forest. Next, please. The 11 Nacimiento catchment, as I mentioned, they are monitored since 2008. Forest operation began in 2009, but then the big Maui earthquake of 27 February 2010 and the mega drought since 2010 are also part of the research. The research is then not only about forest operation and water issues, and we have to adjust it, the research questions and expected results to this changing environment. Since 2020, a new phase of operation began, and pine plantations in 2 catchments were harvested. In the next month, they will be replanted with radiata using 2 contrasting soil preparation techniques. Some published articles below right, our article waiting for the editor's decision. Next, please. Something about the mega drought. Long-term annual precipitation in the Nacimiento area was about 1,400 millimeters before drought. Starting in 2010, the region and most of central Chile is being affected by a severe drought, a mega drought as is known, and precipitation has declined by more than 20%. Prior to 2010, precipitation was higher than potential evapotranspiration, but since 2010 is the opposite. Next, please. Results for a specific catchment. The figure indicates the cumulative decline in runoff relative to precipitation for the 10 study years. The stream flow has declined by as much as 80% in response to interacting multi-decadal effects of forest plantation and severe drought. Responses vary with planted species, forestry treatments, and riparian buffer width. Catchments covered with aging eucalyptus plantation, number 6 in blue, and aging pine plantation, number 1 in brown, behaved differently at the beginning of the study, but ended with the same total runoff after 10 years. In catchment number 11 in green with a mosaic management approach, and number 9 in black with 42% of the area covered with native forest, runoff decline was less pronounced than in the other catchments. Total runoff in catchment number 9 almost double those of catchment number 1 and 6. Modified forest practices, including wider riparian buffers, mosaics with plantation of different ages, removal of exotic trees from riparian buffers, and reduced planted area, may achieve water-saving benefits. Next, please. This research is a joint venture between Forestal Mininco and Universidad Austral de Chile, and is a teamwork. These photos present to the right the Mininco crew, and to the left the Universidad Austral de Chile one. Thank you very much.
Thank you, Andres, and all the panelists today. So we're going to move into during the last 12 minutes or so, a general discussion. So we welcome your thoughts on that. Please enter them through the chat. We'll try and address as many as we can. But keep in mind too, we're in week 6 of an 8-week-long seminar. We're building to what we hope is a community discussion in week 8. So please do keep ruminating on synthesis topics, ways we can cooperate, ways we can work better together, and carry that over from week to week into this final discussion in week 8. But we do have several points that we can address with the whole panel. At one point, there was a question about, do the effects of the harvest technique, either yarding or feller bunchers or other techniques, what are the differences in responses that have been seen with those or even other techniques that have been used on the same experimental forest? Can anyone address that?
Say a few words. So at Casper Creek, we've done both a selective harvest in the South Fork in the early 1970s, and then we did a clear cut in the mid 80s and early 90s in the North Fork, which I had mentioned. And we certainly saw differences between those two. One of the big differences was in the South Fork at Casper Creek, in that early harvest that happened in the 70s. That was before there was strict forest practice rules in place for timber harvesting. And there was substantially more impact for the catchment scale suspended sediment yields. And there were more roads down by the streams. There was less protection in the riparian corridor. So even though it was a selective harvest, the tractor yarding, I think, had a more substantial impact than doing clear cuts. It's difficult to do a direct comparison to the studies because there are always differences between them. The cable yarding experiments had a higher impact for the subcatchments that were cut. We often saw a high suspended sediment response in those subcatchments, but at the watershed scale, they were smaller. And probably the actual amount of wood that was removed per area was a little bit smaller too, across the whole North Fork watershed when we cut it.
Anyone else want to contribute on that? All right. So we actually just got a question in from Jason Leach. He's making the point about, many of these studies are providing foundational knowledge of how we manage forests and what conditions we manage for. But his point is that, even at most, some of our studies are only up to 60 years old. So what do we know about the longer term responses in some of these ecosystems that take much longer for the forest to regenerate to what we would call a mature forest? And I think the crux of this question comes down to, can we extrapolate, or do we need to just keep monitoring in perpetuity to address some of these questions? So appreciate anybody's thoughts on this, anyone on the panel.
Stephen, can I comment this? We're looking at the short rotations of plantation forestry in Chile. 60 years is about 2 rotations or 3 rotations even. So it's much more dynamics. But again, you have different questions and you have a different environment. So which is the long-term effect of drought in this planted forest? So it's complicated to answer your question. Are we going to monitor forever? This is complicated. I think new question will arise very soon in the future.
And Antonia, will you comment too? Because I know that you're working on restoration from non-native species to the forest that would have existed centuries ago, perhaps. Do you have anything to add on that topic?
No, just that yeah, in Chile there has been an important let's say movement towards restoration on private lands, and not only on reserves like the example I put there, because as I was writing in the chat, it used to be a land owned by a timber company, but now it's a reserve. So in the reserve, they want to get rid of the eucalypts as normal. But also there's a restoration going on private lands owned by the companies that Andres and Francisco presented, because they have commitments in front of FSC to restore forests that were converted from native forests to plantations after 1994. So restoration is very important in Chile, and it's very important to monitor the recovery of stream flow after this process.
I believe I cut somebody off. Please continue if I didn't allow you to speak.
I was just going to say that part of the issue is that we haven't seen in many places actual recovery. I think the word recovery is not appropriate in a lot of places. So on the one hand, I think we have to keep monitoring forever, as naive as that sounds, because we're not even sure that there's actual recovery. But I also think that there's a lot of value in cross sites comparisons, like Denmore has initiated, like that what we can learn by comparing different catchments, I think is very valuable. And for instance, while we know that we've seen low flows being very dramatic in the summer in Oregon with Douglas fir, despite variable geology. So we saw it in ALSE, we see it in the Andrews. I think there's a lot of value in trying to understand what happened with other species, like what we have in Casper Creek with another tree. So I think that we need to continue monitoring forever, but also we need to take advantage of cross comparisons and what we can learn from that.
And maybe related to that too, does anyone have sites that used to formerly be chestnut or the Castanea family or genus? Because you think too about a keystone species that now is gone because of disease, and that we'll never get back to that. So this is another interesting point when it comes to what is long-term monitoring yield, and what are the chances of restoration. Kenton, is chestnut any part of your past in Kentucky?
Yeah, certainly it would have been a historically significant component in our forests for sure, in Robinson Forest. And I think in addition to that, so, in this question of like, what kinds of data do we have reaching back like far enough to understand very, very long-term trends? In addition to those kinds of dynamics, like species composition dynamics, which are continuing to flux, because, for example, right now we've got hemlock that we're losing hemlock in our forests because of hemlock woolly adelgid, and I see Chris Barton just commented that as well in the chat. In addition to that, I think climate change, it also is going to make it really difficult to explore and think about like to look back in order to be able to effectively predict the past. I was going to comment one possible site of historical data that reaches back beyond the start of our catchments would be like oral histories and indigenous knowledge. But even those, those sites of knowledge won't necessarily be able to take into account some of the very large scale changes that we're experiencing right now. So I think it's a really complicated question. It's really important, but it's really complicated.
Thank you. I think I want to shift gears and get to a bit of a different topic, and it's on extreme weather events. In particular, somebody was asking about cloudburst phenomena. Have they been observed at your watershed, and what are the effects? What are the lessons that we could learn from studying such events? Kenton, I see you shaking your head. Do you want to chime in first?
Just that's on our list of things to explore. So I unfortunately have nothing specific to say about it, but we are really interested in exploring the intense changes of intense storms over time in our catchment. So stay tuned.
Anyone else have anything to offer on that topic? Or perhaps even the implications for forestry and, products that were intended to come off the forest that would be affected by such events. All right. Kevin Ryan is asking to presenters from Chile about the current legal framework and enforcement for forest management. Do your studies suggest any specific changes that are needed to laws and the legal framework?
Francisco, are you going to answer?
Yeah, I'm going. But yeah, sorry. So yeah, I have a question from Kevin Bishop. So yes, inside the company, we're changing some things in terms of silviculture, but are more in terms of on volume and water resources than legal. The legal framework is not so strong in our country. So we have a law, but the biggest, the biggest law is the FSC. FSC says whatever, the forest company follows that the FSC, framework. But legally, there are some things in native forest that you can cut, etc. But I think the work that Antonio is doing, plus some others inside the forest companies, I think it should be go further and try to get some, Antonio said that, some legal framework in terms of where do you have to put plantation, where you don't have to put plantation, what the communities nearby plantations said. For example, we have in Arauco some places that we are not allowed to plant ukes because the people say, I don't want eucalypts, so just plant pines. So we are changing the things, and we're trying to put more efforts also in restoration. So the Antonio example is perfect for what we're doing now. But yeah, it's difficult when you are in a research organization, because you are saying, yeah, we need more native forest. But also you have in the other hand, you have the money, the plantations. So they need more plantations, they need more volume because the pulp and et cetera, et cetera. And yeah, it's kind of difficult, but legally, we don't have too many stops in terms of, we have, for example, I don't know, I think it's 500 hectares, the maximum area that you can clear cut. So you clear cut in pieces. So you can clear cut, I don't know, 1,000 of hectares, but because they're separate for X meters, you can do it. So the performance is not that bad for the FSC. Yeah, it's more difficult.
Thank you very much. All good points to think about. At this point, I'm going to turn it over to Julia to give us some concluding remarks. Thank you, everyone.
Can I say just very briefly, now in this moment, there is a discussion about some standards for clear cutting, and the size of the clear cut area and some of the method of clear cutting are under discussion. So perhaps there will be something new in the short future.
I'd really like to thank all of our panelists and presenters for excellent presentations. Collectively, they provide strong evidence that catchment studies are very dynamic and still really essential to a number of aspects of land management, ranging from the effects of mining to contemporary and past forest practices. And I hope that we will have continued opportunity to talk about ways to synthesize more of this work in week 8, which Jamie and Stephen will lead. So thanks to everyone for signing in. We had excellent attendance. Thanks for the excellent questions and the wonderful conversation. And thanks to the presenters.
And thanks, Julia, for moderating. And just one last word, to be looking for a survey. We've gotten lots of ideas for week 8, but we're going to post a very brief 1 or 2 question survey to get your ideas, solicit ideas from all of you. And we will be putting them together, taking the questions from these weekly meetings and putting together a good discussion on week 8. But week 7 is coming up with urban and agricultural catchments. So please tune in again next week. Thank you, everybody.
Thank you.
Bye.
Bye-bye.